Hello, my name is Kambiz Bazari. Many total hip replacements fail because the surgeon cannot properly press fit implants. Vibratory insertion of orthopedic implants can ensure proper press fit and prevent these hip replacement failures. The orthopedic medical device industry is a $50 billion industry, and revision surgery accounts for up to 30% of that industry. Total hip revisions are necessary because when hip replacements fail, patients experience pain, suffering, and loss of functional mobility. Total hip replacements primarily fail due to aseptic loosening, and there is a host of secondary causes of failure, including malpositioning of components, metal debris, osteolysis, and infection. No one has talked about this, but I believe many of these primary and secondary complications are the result of the surgeon's inability to properly press fit implant. Our current technique involves using a mallet to repeatedly impact an implant into position within bone. And the goal of this technique is to obtain optimal stability of the implant through interference fit. Interference fit is achieved when the implant is properly grasped within the cavity, and proper grasp exists when the implant is fitted neither too tight nor too loose. So you see, our current technique is a bit of a Goldilocks problem. It requires the surgeon to insert the implant deep enough to obtain sufficient fixation, yet avoid fracture from inserting the cup too deep. Thus, the surgeon has to identify and reach an endpoint that corresponds with optimal primary implant stability. The problem is that this endpoint is elusive because it can only be determined qualitatively through the surgeon's auditory, visual, and tactile senses. So the surgeon has to essentially look at the depth of insertion, listen for the changes in pitch, and feel for the changes in the bone's grip of the implant. However, because 80% of the surgeons who perform total hip replacement perform less than 10 per year, they may never develop the qualitative sense that they need. And this may be why surgeons either press fit the implant too loose, which leads to aseptic loosening, or too tight, which leads to fracture. When surgeons play it safe and forego press fit fixation by over-reaming and using screw fixation, then they cause a secondary set of problems, including metal debris, osteolysis, and polyethylene wear. It is known that 75% of total hip replacement failures occur due to aseptic loosening. I believe the surgeon's inability to obtain proper press fit causes many of these failures. But if the surgeon could reliably achieve press fit fixation, it's possible that the incidence of loosening would decrease dramatically, thereby lessening the number of hip revision surgeries. The current cost of hip revision surgery in the US is unknown because there's no national total joint registry. But we can look at past trends. Based on a 2002 study, there were 37,000 hip revisions done annually at an average cost of $31,000 per revision, with a total cost of $1 billion. And hip revisions don't do as well. They have a higher incidence of morbidity and mortality and provide less functional improvement. Because there was a 50% increase in the number of hip replacements between 1994 and 2004, it's reasonable to expect a similar increase between 2004 and today. This may mean that the current cost of hip revision surgery is several times what it was 20 years ago. So if we want to solve this problem, how would we go about it? Any solution requires us to accept an uncomfortable truth that the surgeon's brain is not very good at determining optimal press fit. And this is true regardless of the surgeon's training and level of experience. If we can accept this, it's logical for us to desire something beyond the surgeon's brain, and that is a system that finds optimal primary implant stability quantitatively rather than qualitatively. We also have to address the fact that the process of assembling implants into bone is non-standardized, and we have no tool that allows the surgeon to modulate force to meet a standardized process. Best fixation short of fracture is the quantitative system that we need because it tells the surgeon how hard to hit and when to stop impacting. It also provides the metrics that make standardization of implant assembly possible. Now, standardization does not mean a single force value that is appropriate for everyone. This is because optimal implant stability is a relative value that varies significantly from patient to patient, depending on age, sex, and physiological condition. Thus, standardization would mean identifying the sweet spot of press fit that is unique to each patient. I named this concept Best Fixation Short of Fracture. It was presented at the 2019 Toronto ISDA meeting, and it was selected to receive the annual Shark Tank Award. These are my patents that are associated with this project, and that presentation or version of it could be viewed on my website here. It's important to understand what I mean when I say the process of assembling implants into bone is non-standardized. In any industry, there's always standardization for design, material, and assembly. However, in orthopedics, we have standardization for design and material, but not for assembly. Essentially, when surgeons press fit implants into bone, they're left to their own discretion to determine when they have obtained optimal implant stability. This is obviously not the case in the aviation and automotive industries. In these industries, assembly is a highly standardized process with tools that help the mechanics precisely apply predetermined levels of force. No one would accept a plane that was assembled at the mechanic's own discretion, so why should we accept an implant that was assembled that way by the surgeon? To utilize a quantitative system, surgeons will need a tool that allows them to modulate force. Right now, surgeons have no such tool because the mallet they use does not give them control over either the magnitude or the direction of force. And because surgeons cannot modulate magnitude of force, the patient is subject to the negative effects of overimpaction. It's universally agreed that overimpaction can lead to fracture. However, there are a host of other factors that are not well understood. Overimpaction may be responsible for cell death and loss of vascularity, which may lead to poor bone ingrowth, which may lead to aseptic loosening. And because surgeons cannot control the direction of force, the acetabular implants are subject to malpositioning, which may lead to polyethylene wear and dislocation. Surgeons cannot control the direction of force because they lock the implant into position with each blow of the mallet. This makes adjustment of implant alignment impossible. I've described this problem as implant stickiness, and it's important to realize that no monitoring technology, no matter how sophisticated, has ever solved this problem. The Best Fixation Short of Fracture project solves part of this problem because it tells the surgeon how hard to hit the cup and when to stop impacting. Thus, within this system, the surgeon now has control over the magnitude of force. The surgeon still needs better control over the direction of force, and a vibratory insertion tool would provide this directional control with the added benefit of using significantly less force. A vibratory insertion tool could be either handheld or a part of a larger robotic platform. However, right now, neither cater to the primary needs of orthopedic surgeons. And this may be because most robotic platforms are designed with the general surgeon in mind. There are profound differences between general surgery and orthopedic surgery. General surgeons primarily dissect, cut, cauterize, and suture, but they do not apply force. Orthopedic surgeons often apply force to press fit implants into bone. And safe application of force requires them to have a tactile sense of how much force is being applied. I call this sense haptic connection. When you have it, you can feel the resistive force from the patient's bone, and when you don't have it, you cannot. No robotic platform offers any tool to enhance haptic connection. Current robotic platforms provide haptic restraints, which enable cutting with greater precision. They also provide guidance for alignment. However, there's no tool that aids the surgeon with the application of force. I believe the current robotic platforms that provide greater precision with cutting and alignment actually sacrifice the haptic connection that the surgeon needs for implant installation. Haptic connection is lost when the surgeon gives up control of the impacting tool to the robotic arm. When the robotic arm holds the impacting tool, the surgeon can no longer feel the resistance to the force that he's applying. A truly innovative solution would maintain haptic connection while providing greater control over alignment. In many ways, orthopedic surgeons are like the Greek figure Antaeus. Antaeus had great strength so long as he was grounded to Mother Earth. However, all his strength was lost as soon as he was lifted off the ground. Orthopedic surgeons cannot be lifted off the ground. We must stay grounded, and we must maintain our haptic connection to the patient. A current market solution to this problem are handheld tools that use a process known as automated percussive impacting. I believe these tools use a motor to drive a compression piston to move a traveling striker from a start position to an end position. Each successive strike imparts force onto a surgical implement. I believe these tools generate around 5,000 newtons of force at 6 hertz. So complex energy storage mechanisms are used to generate high magnitudes of force. And energy storage mechanisms can be heavy, and maybe why some of these tools weigh between 8 to 9 pounds. And although automated percussive impacting has allowed surgeons to consistently deliver the same amount of force, I believe the amount of force delivered is universal for all patients. And the method by which the force is delivered is too similar to discrete impacting with a mallet. I believe the tool does not allow easy adjustment of implant alignment. And most importantly, I believe the tool violates my anterior rule because haptic connection is lost at such heavy weight. My solution uses something called driven vibrations to insert orthopedic implants into bone. It could be used in a handheld tool or robotic platform. Vibratory insertion will not only drastically decrease the magnitude of force required for implant installation, it will also allow easy control of the direction of force, allowing us to obtain the exact alignment we desire while maintaining haptic connection with the patient. We have seen that with vibratory insertion, a cup could be inserted into bone with as little as 300 newtons of force, which is less than 1/10 the amount of force typically required using standard technique with a mallet. I believe this could be attributed to the frictional phenomena at the interface. When the implant is vibrating at higher frequencies, it has a higher exposure to a coefficient of kinetic friction, which is lower than the coefficient of static friction by as much as 30 to 50%. This may mean that the resistive force to insertion is lower by 30 to 50% with vibratory insertion technique. And because vibratory insertion decreases the static hold of bone on the implant, there's now the possibility to have greater control over alignment during the insertion process. And this is because bone is much more flexible as a dynamic system when vibrating than as a static system when impacted upon. And in this dynamic system, it's not possible to simultaneously insert and align the implant into the desired position. I call this concept float. The vibratory insertion tool maintains haptic connection because it could be made under 2 to 3 pounds. This tool can be light because it doesn't need complex energy storage mechanism or a large motor. These components are unnecessary to have a high frequency, low magnitude force. Vibratory insertion can offer so much because it's truly an innovative solution in a way of applying force to install implants into bone. A vibratory insertion tool uses driven vibrations rather than discrete percussive impacts to install prostheses into bone. It uses an oscillation engine to create an original pulse wave. This pulse wave has its own amplitude, frequency, wavelength, and direction. This wave then transfers through a series of supports and creates a series of secondary pulse waves. These secondary pulse waves eventually reach the implant and create vibration of the implant, which allows the implant to be installed into bone without impacts. There's a desynchronization process of the oscillations that occurs between the supports, and each desynchronized pulse wave develops its own pulse frequency, wavelength, amplitude, and direction. I thought that if 14 humans can walk a 10-ton statue without using a bulldozer, maybe orthopedic surgeons could float the acetabular cup into position without using 10,000 newtons of force. I saw that when the statue is oscillating to and fro, rather than being pushed straight forward, a different set of frictional forces were being used. If those frictional forces could be used in that setting, then orthopedic surgeons could be using them in hip arthroplasty or some version of that set of forces. You may be asking yourself, why couldn't the automated percussive impacting tool be made to vibrate faster? And the answer lies in a limitation of classical mechanics. Whenever you're constrained by a constant level of energy and a given mass which you have to move, frequency and amplitude are inversely related to each other. So if you want high magnitudes of force within these constraints, you cannot operate at high frequencies. You have to choose between one or the other. And we all see this when we have to choose between speed and torque when we ride our 21-speed bike. So if you want a lightweight, handheld vibratory insertion tool that maintains haptic connection and can operate at high frequencies, you're going to have to give up high magnitudes of force, complex energy storage mechanisms, traveling strikers, anvils, and compression pistons. The good news is that you do not need high magnitudes of force to install implants into bone. Smaller tools with smaller engines and no energy storage mechanisms can achieve higher frequencies and be very efficient in installing implants into bone. This is our current technology in 2020. Essentially, surgeons use a 2-pound mallet to deliver between, on average, 3,000 to 6,000 newtons of force. And that's very heavy to install the acetabular cup into bone. And it's not infrequent that surgeons may deliver up to 9,000 to 10,000 newtons of force. These are our original vibratory prototypes. This is a pneumatic prototype which produces only 300 newtons of force and vibrates at 60 hertz, and our electric prototype which produces about 800 newtons of force at 60 hertz. And these are just as effective in inserting implants into bone, if you think about it, using 90% less force than our current technique. I also believe that vibratory insertion provides the possibility of further research and development. If ultrasonic vibrations could be superimposed on driven vibrations, then the elastic nature of bone could be amplified. This could excite certain mode shapes and compression cycles, which could be leveraged to decrease the static hold of friction. This would relieve interference fit and potentially dramatically reduce the amount of force required for implant installation in all of orthopedics. Superimposition of ultrasonic vibrations in other industries has decreased force requirements for press fitting by as much as 80 to 90%. It's also possible to create additional dimensions of vibratory insertion. The tools that we've envisioned right now are vibrating longitudinally in the z-axis, but they can also be vibrating rotationally in the z-axis. In the future, it may be possible to include motion in one or more of 6 degrees of freedom. And this would mean having vibrations in both longitudinal and rotational direction in any or all of these axes. I've named this concept superfloat, which I believe will allow the surgeon to place the prosthesis in exact alignment with ease. These are my contributions to the vibratory insertion concept, which include 4 US patents and 1 European patent. Vibratory insertion with IME technology has a potential to make robotic platforms and computer navigation obsolete. All you have to do is calibrate the axis of the tool with the axis of the pelvis. Then you can monitor implant insertion and alignment in true real time with a simple handheld tool without any bulky equipment in the OR space. And these are my patents and contributions to this concept. Driven vibrations could be used for bone preparation, and I believe it's distinctly different than percussive impacts that are currently used to prepare bone. I believe this method will provide significant improvement in the ultra-fine preparation of the femoral and acetabular cavities to produce a much better press fit for hip arthroplasty. These are my contributions and patents for this concept. I'm already engaged with the engineering department of University of Minnesota with the best fixation shoulder fracture project. I'm now looking to develop the vibratory insertion project. I anticipate $1 million in further funding is required to develop and test additional prototypes. The prototypes will be tested in various bone substitutes and cadaver bone. Another $1 million will be needed to develop a medical grade tool that will pass as 510(k) pre-market notification. I believe once the tool passes regulatory requirements, it will be demanded by surgeons, hospitals, and insurance companies, and maybe even mandated by the government. I anticipate the tool will cost no more than $5,000 per unit to produce. It could be either sold or leased. The unit may have a lifetime of 2 to 3 years or an expanded lifetime with maintenance and service contract. There may be up to 10,000 hospitals and/or surgery centers which may each potentially make a capital purchase. The tool will be open source and will have disposable adapters that will allow use by all medical device companies for all implants. And the disposable adapters could be produced at very low cost and retailed at a high premium. Total hip replacement procedures are the immediate market for vibratory insertion tool for both the femoral and acetabular components. And the eventual market will expand likely into the knee and shoulder implants and ultimately into the trauma-related implants. In 2024, it's anticipated that there will be 400,000 total hip replacements performed in the United States. This number may be as high as 800,000 worldwide. 80% of these procedures will be performed by surgeons who perform less than 10 per year. Knowing what we know now, will patients still want their implants installed with a mallet? Or will they want a tool that places their prosthesis in exact alignment with minimal force? Will surgeons continue to use haphazard techniques, or will they demand a more reliable and safer tool? Will hospitals and insurance companies continue to incur the cost of revision surgery, or will they mandate the use of a tool that reduces revision surgery? Will medical device companies continue to have their implants installed with a mallet, or will they invest in new technology that improves patient outcomes and strengthens the reliability of the implants? Time has come up to give up the mallet. What will replace it? Thank you.